All right. Hello and welcome to the last week of class. You made it. So all that I'm going to do this week is go through these slides and give you a review for the final. We'll see how long they take. I'm going to definitely make sure that they fit into a 2-lecture week, but who knows how long it'll take us. So just remember, this is all for you, and you can fast forward and do whatever you want. Okay, so let's get started with the first chapter that will appear on the test, so the one about induction and recursion. Okay, so let's go over all this stuff. I'll make new slides as needed. Let's just go crazy. So the first thing that you learned about in this chapter was sequences. Okay, sequences are just a way of specifying numbers and how they increase, right? Usually it's a sequence of numbers, and so we have, like, I don't know, 4, 8, 12, 16, 20, on and on forever. That is an arithmetic sequence because it's always increasing by a common difference, and this is positive 4, okay? And then there's an initial value. So this is a sequence. It's an arithmetic sequence because it keeps on increasing by this difference, that common difference. Okay, and so if you were to label, like this is your sequence, maybe you could give it a name. It's called S, and so this would be S sub 0, S sub 1, and you can talk about the elements of the sequence that way, S sub 2, S sub 3, dot, dot, dot. Okay, so each sequence has an index and a corresponding element of the sequence, and you can start the sequence at whatever number you want. Usually it's 0 or 1. Okay, so that's arithmetic sequences. Let's now talk about geometric sequences. And so those are almost exactly the same, but instead of a common difference, it's like a common factor, whatever the fancy word is. So I can have 1, 2, 4, 8, 16, 32, dot, dot, dot. This is a geometric sequence because each time I go to the right, I am using my previous value and I'm multiplying it by 2. Okay? So instead of plus some number, it's times some number. Okay? And it could be a fraction. Could be a negative number. Same for these. Okay? Could be minus. Doesn't have to be plus up there. Times 2, times 2. So this is a geometric sequence, and everything is increasing by that factor. Okay? So that's sequence stuff. And once you have a sequence, once you have a list of numbers, you can talk about, are they decreasing, non-increasing, non-decreasing, or increasing? So let me show you examples of all of those. So a decreasing sequence is always getting smaller. It's like 5, 4, 3, 2, 1. Also, sequences don't have to be infinite. They could be finite. This could be the entire sequence. It's totally fine. This is a decreasing sequence because it's always getting smaller. Okay? Always getting smaller. Whereas a non-increasing sequence can, like, stutter for a little bit and then get a little bit smaller. So like 5, 5, 4, 4, 4, 3, 2, 1. This is not strictly decreasing because it sometimes stays the same, but it's definitely not increasing. You see how that's working? A non-decreasing sequence is the opposite of increasing, so let me do that one first. Increasing is, of course, getting bigger. Always getting bigger. A non-decreasing one is just never getting smaller. So it could be 1, 1, 2, 2, 3, 3, 4, 5, something like that. Okay, so that's all of these, and I kind of ordered them in a logical way. Hopefully that makes sense. Okay. A nice example of sequences is this one. We can define a sequence like this for n greater than or equal to 1. So a of 1, a of 2, a of 3, those have values, and it's an infinite sequence. So apparently, a of 1 is 1 squared minus 4 times 1, so that is negative 3, right? 1 squared minus 4, yeah, 1 minus 4 is negative 3, cool. And then we have this one, a2 is n squared minus 4n, so 2 squared minus 4 times 2. So that is 4 minus 4 times 2, which is 8, so negative 4. a3 is this one squared, so 3 squared minus 4 times 3. So that's 9 minus 12, right? I think. Let's just confirm all this. I don't want to be telling you incorrect information, but I think you can understand how to generate a sequence with all this. -3. Okay. So this is a weird looking sequence. Let's do a4 as well. 4 squared minus 4 times 3. Now this is positive 4. A5 is 5 squared minus 4 times 5. Now it's 5. A6 is 6 squared minus 4 times 6. It seems to be always getting bigger at this point. But oh man, it got smaller, increased, and then kept increasing. That's crazy. So this is, I don't think, any of these, right? It's not strictly decreasing. It's not non-increasing because sometimes it gets bigger. It's not non-decreasing because sometimes it gets smaller, like this. And it's not increasing because sometimes it gets smaller. Okay, so it's none of them. This sequence is none of the above. Isn't that cool? So that's sequences, and you can define sequences using this thing called recurrence relations, recurrences. The common example is the Fibonacci sequence, so like f of 0 is, I guess we can define it to be 0, then f of 1 is 1, and then f of any other n that's greater than or equal to 2, is f of n minus 1 plus f of n minus 2. And that's your recurrence, because you're defining the next element of the sequence in terms of the previous few. Okay? That's the idea. That's all a recurrence is, and you can define arithmetic and geometric sequences that way as well. Okay? An example, what are the first 6 terms of the following sequence? Yeah, well, we have 4 and 5, that's for sure. And then the rest are the product of the previous 2. So this one, C3, is C of 2 times C of 1. This is C of 2, or sorry, C of 1, C of 2. And so the next one's 20. So C of 4, C of 5, C of 6 happens this way. So 5 times 20 is the next one. See how I'm reading that? 100. This is apparently 2,000, right? 20 times 100, 2,000, and then 2,000 times 100 is 200,000. So those are the first 6 terms of the sequence. Okay, so that's recurrences. You can just define your sequence in terms of itself. That's all, not too bad. Summations are a nice one. That's where you have that sigma that is letting you have some expression here, and then the starting value and an ending value. And it's talking about a sum of a bunch of stuff. So here's my fun example. Jeff Bezos, very rich man, has way too much money. He makes $3,715 per second. So let's use a summation to discover how much he makes in a day, just to represent that number, whatever it may be. Okay? So the idea is you just say, we want to sum 3,715. How many times? Well, how many seconds are there in a day? You start your I at 1, and then we go to, I guess, 60 times 60 times 24. Yeah? So that's how much money that Jeff Bezos makes in a day. You just take this and you add it to itself, because there's no I here. We're not using I, we're just using it to tell us how many times we sum this number that many times. Okay, that's how you read that. And then here's another example. Let's represent the sum of the first n elements of the form 2 times 13, 3 times 23, 4 times 33, on and on and on. The next one would be what? 5 times 43, right? Not plus, times. 6 times 53. Okay, so we need to figure out what is the secret here, what's going on. So, always a sigma. What are we're multiplying 2 things against each other. I'll figure out those. It's common to use I, and we might as well start at 1. Okay? So, we want to sum the first n elements, so we'll just go from 1 to n. That'll make n things in our summation, n things that we're summing together. And then we always want to sum what times what. If this is a of 1, how am I going to use this 1? This is what our I is. I equals 1 here. How will I generate this? I equals 2 here. I equals 3 here. How will I generate this from I? Okay? And it looks like it's I plus 1 times, let's go for this one now, 2 times 10, I times 10 plus 3. Yeah? That times that. I think that should work. Because if I is 5, this will be 6 times 50 plus 3 is 53. Yeah, looks like it's working. Okay, so that's summations. I'm just going to go light speed because there are so many things to get through. Let's do induction now. Okay, so that was like the meat of this chapter. We were all building up all this stuff before so we can get to induction. That's one of the most important topics of this class. So remember that when you're doing induction, you're proving something. You're proving that something is true for all n. You're proving a for all. Okay, for all n, and the natural numbers usually, or like the positive numbers starting at a certain value, p of n is true for some predicate p. Okay, that is essentially what you're doing with induction, and the way you do it is you have a base case and an inductive case, and that gives you the proof. The base case is saying, I know how to solve the problem p of 0. I know that p of 0, that predicate, is true. And then the inductive case is proving that if I know p of k for any k, then I know p of k plus 1. I can prove it. And this is for all k. And the reason that this works is you start out with p of 0, and then you can use the inductive case rule to, I guess it's the inductive step, right? You can use the inductive step rule to go from, okay, yeah, I'll just plug k in as 0. That'll get me p of 1. I can use this to make p of 1. Then I can use this in the inductive step to make p of 2. And then I think you can see how you're going to make p of any number. You've proven p for every number. That's how it works. And so when you're proving the inductive step, remember that this is a proof of an implication. You have something you get to assume, right? So your inductive hypothesis is just what you're assuming. You get to assume p of k to prove p of k plus 1. Okay, it's just a direct proof. Cool, huh? So that is the ingredients, and let me just show you a simple example. We'll prove that this classic summation 1 plus 2 all the way to n is always equal to n plus 1 times n over 2. Okay, so let's prove this. Proof by induction. Base case, we'll prove that like p of 1 is true. If we have just one thing in our summation, 1 all the way to 1, so it's just 1, sum of all the numbers, with just 1, I guess it's probably easier to use summation here. Sum of all the i's starting at 1 and ending at 1, that equals 1. Okay? And that's easy because you can just write it out. There's only one number to sum, and it's 1. Okay? So that's proof of the base case. Check. And then the inductive step works like this. We have, we get to assume p of k is true. Assume p of k, which means that's equivalent to assuming that this is p of n, right? We get to assume that 1 plus 2 plus dot 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 all the way to k, right? That's we're plugging it in, equals k plus 1 times k over 2. Yeah? That's what we get to assume, and now we have to show that p of k plus 1 is true. That 1 plus 2 plus dot 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 to k plus 1 is equal to k plus 2 times k plus 1 over 2. And so let's bring this onto a new slide and go from there. Whee! And let's move it up. There we go. Get rid of that. Let's make it a blank slide. Okay, so let's show this using our inductive hypothesis. And the beauty is, oh man, I have this sum inside of the sum that I need to prove. So I can take that out and say that, okay, I know by the inductive hypothesis that 1 plus 2 plus dot 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 plus k plus 1, that's equal to, by the inductive hypothesis, IH gives us this. We know that that's equal to this. I get to replace that part with the inductive hypothesis, right-hand side. k plus 1 times k over 2. And then I have still plus k plus 1 over here. Okay, that's the key. And then I just have to show that it's equal to this now. And so I guess what we should be doing is bringing this over so we can make common denominator. So this is k plus 1 times k over 2 plus 2 times k plus 1 over 2. And so now I can bring them together. That is k squared plus k plus 2k plus 2, right? I think that's working. Over 2. Let's keep going. This is k squared plus 3k plus 2, and I'm pretty sure that this will factor the way we want it to, right? It factors into this. Because it's k squared plus 3k plus 2. Yeah. Cool. K plus 2 times k plus 1 over 2, which is what we wanted to show, and that proves the inductive step. Okay, end of proof. So because we showed both of these things, we know how to get a proof for any number. And so it works for every number. That's the beauty of induction. Okay, hopefully that makes sense. Please yell at me if you have any questions about any of this stuff. Remember that I have office hours during this last week of class when you'll be watching this. Okay, time for recursive set definitions. This is fun. So induction and recursion, they're kind of similar, but ever so slightly different. Induction is like bottom up. So you're starting from 0, going bigger. And then recursion is like top down. You're breaking down into smaller pieces, something like that. Okay, so that's doesn't really matter for anything for this class, but just for your knowledge. Okay, so let's just solve this problem, and we'll get acquainted or reacquainted with recursive set definitions. So here's my set S. I'm defining this set S recursively or inductively. I guess we could say. I think induction is the right word here, but who cares? Your book says recursive. So this is our set S. It is something. We're not sure. It's a set of things. And we have some rules, though, that tell us what's in S. And we want to discover the strings of length at most 3. All right? So here's the base case. We know immediately, the definition gives us that the empty string lambda and the single character B is in S. And the alphabet is AB, by the way. Okay? So you can only have strings made up of A's and B's, and also the empty string because it's in the language. Okay, so we have these two now, and then we can use recursive rules. It's saying that, okay, if we have something in S, so you can take anything that's in S out and use it with either of these rules. So if you have something in S, you then have that thing with A at the end, concatenated. You also have that thing with AB at the end, concatenated. Okay, that's how you make bigger things. So, for example, lambda is in S. So I can use this rule to make lambda A and lambda AB. See that? And remember that lambda is the empty string. So this is really a single character. This is really just 2 characters. Okay, so these get to be added. These 2 strings get to be added to our cloud of S, right? And we get to use the recursive rule for everything now. Even the stuff that we just added. If this thing isn't in here, it gets to be the X in this rule. All right? So let's try it with B now. Let's let B be X. So we know that BA is in there. We know that BAB is in there. All right? Now let's do it for A. We know that AA is in there. We know that AAB is in there. Yeah? That's the beauty of it. Okay, which ones haven't we done? These are the only useful ones because we're trying to look for the strings of at most length 3. So it makes no sense to use the rules with these because they're always going to make us have a length 4 string. So let's use these 3 now. So we know from BA, following these rules, that BAA is in there. And then this one would make a length 4 string. It would make BAAB. It's still in the set, but we just don't care about it in our answer. So likewise, AB makes, what is it? ABA, and then AB, AB, and then AA finally makes AAA and AA, AB. Okay, hopefully you see how I'm using that. I'm just plugging it in for X. And then I have length 3 ones. I don't want to use the rules to make bigger ones. And then I have these big ones, which I'm not going to count in my answer. So really, the answer is all the strings of length at most 3. There are more things in this set. It's an infinite set. It gets to have infinite size characters, infinite size strings. But I've stopped just so that we're done. Okay? All of these things, underlined in green, are the answer. Okay? Underlined in green, that's where the answer is. Dun dun dun. All of these are strings of length less than or equal to 3 in S. There's more, but that's all we need. Okay? So there's that many. Are there any duplicates? That's the next thing. It doesn't look like it. BAB, AAB. I think we're good. So, yeah, that's what happened. It made all of those things. Isn't that fun? Okay, so that is all the strings of length at most 3 in S. That's how you use a recursive definition of a set. So just remember that. And finally, that brings us to recursive algorithms, which we can prove correct using induction. Isn't that nice? So the common example is factorial. Let's just do it in C++, because why not? Int factorial of a number n, that is equal to, well, base case, if n is 0, return factorial of 0 is always 1. Otherwise, return n times, I guess it's a star in C++, right? N times the factorial of n minus 1. And that is the recursive definition of the factorial function. And it's just following these rules, like n factorial equals n times n minus 1 factorial. And the base case, 0 factorial is always just 1. Okay, so that is factorial, and we talked about like running time analysis for recursive algorithms. Let's find a recurrence for the number of operations for an input of size n. So this is n. Dun dun dun. Well, let's find it. And do I want to give myself space? Yeah, sure. Let's write it right here. Okay, so the idea is T of n, what's the number of operations for an input of size n? We do, usually, we talk about the recursive case. Okay, so you have to do like a multiplication and by a number, and you have to return it, so it's like 2 basic operations or so. And then you have to call fact of n minus 1, so you got to do that first to get the answer. That's T of n minus 1. And then we have, let's see here, plus theta of 1, because you just have a constant number of stuff left. Okay, so this is the recursive call. And this is everything else. This is like the times. This is like the return. It's just a constant amount of work. Okay. So that is the recurrence relation, and if you remember the master method, let's see if it applies here. Oh, I forgot to pull up those slides. Let me go and do that, and I'll be right back. All right, I am back. Here are those slides. So does our factorial recurrence look anything like this? We got a theta of something, theta of 1, which is just d equals 0, right? But we don't have this kind of factorization of the n. We don't divide by anything. We don't even multiply by anything. So master theorem, or it's also called master method. Let's just keep it as theorem, just to make it so that your book is not lying to you. But you can say either, really. You can't solve it with the master theorem because it's more for divide and conquer algorithms, ones that divide their work into pieces. Okay? So that doesn't apply, unfortunately, but you can just make a tree. It's like, okay, T of n, that is equal to, you have theta of 1, and then I need to do whatever T of n minus 1 is. N minus 1. And what's that but just constant work and T of n minus 2. And eventually I'll get to the bottom. It's just going to be a bunch of theta is of ones, but it's going to be of like n height. Okay, so it becomes theta of n. It's a linear algorithm, and that makes sense because it's just getting smaller one by one. So yeah, that is the idea there. And let's prove that this function, this factorial function, is correct using induction. So here's the function. Let's make sure that it makes sense to ask this. Like the theorem is, what's our theorem statement? It is fact for all n, like this is what we want. For all n, fact of n equals n factorial. That's all. That's what we want. Our factorial function is the same as the real life mathematical factorial operation. Okay? That's what we're trying to prove here. And so now, hopefully, the base case and the recursive case makes more sense. Or inductive step makes more sense. So the base case is the same as the base case of the recursive function. It's like, okay, let's prove, like this is, let this be p of n, we prove p of 0. Okay? So that's saying that factorial of 0, or we need to show that factorial of 0 is equal to 0 factorial, the real life thing. This gives back 1, this gives back 1. Yeah? So yes, it checks out. Base case is true. And then we have the recursive step, or inductive step, sorry. We assume p of k plus 1, which is, or sorry, p of k, which is factorial of k is equal to k factorial. And then we need to show, factorial of k plus 1 is equal to k plus 1 factorial. Yeah? That's what we need. So, here's how we do it. We're calling fact with k plus 1. It's going to give back, this side gives back k plus 1 times factorial of k. Okay, and that's all well and good. And then we can use the inductive hypothesis here, because this is going to be equal to, we get to assume that it's equal to this, equals k plus 1 times k factorial. Isn't that useful? And this is, of course, just equal to k plus 1 factorial. And that was what we needed to show. That is equal to that. Check. And so that proves the whole thing. That proves that the factorial function that we wrote is exactly the same. It computes the same value as mathematical factorial. Okay? So hopefully that's making some sense. And it all falls together. Like the base case of the recursive function becomes the base case of the inductive proof. The inductive step talks about the recursive case. That's all. Okay, so that is induction and recursion in a nutshell. Let us continue to, let's make sure I'm doing this right. Let's continue to graphs. Okay, so let's talk about graphs and maybe trees, and that should be enough for today, I think. So graphs can be either directed. They got a bunch of vertices and edges, remember. Vertices and edges. They could be directed with arrows, self-loops, parallel edges. Could be directed, that means arrows exist, or they could be undirected, self-loop, parallel edge, and there's just lines. It's like you can go either way. That's the idea. Okay? So vertices are just points in the graph where you could travel to, potentially. Edges are the things that connect the vertices. They could be have arrows or not have arrows. The degree of a arrow, usually we use this, or sorry, the degree of a vertex is the number of edges coming out of it. If it's undirected, I think we've only talked about this in the undirected case, so let's just talk about undirected graphs right now. The degree of this vertex is 2, because it's got 2 things coming out of it. Okay? That's the idea. That is degree 2. That is the point. So then we have the idea of a subgraph. That's just like taking a piece of another graph and, oops, making another graph out of it. So this is a subgraph because I'm taking a few vertices and edges. That's all. Okay, so that's all the terminology. Do look at the slide. There's a lot going on here. Look at the book, but this is like a nutshell version of all this. I do want to talk about these 4 terms, though, because they are hard in my mind to keep straight, so I can only imagine how hard they are to keep straight in your mind. 99% of the time in computer science, we care about paths and cycles. Walks and circuits, they don't really cross our mind. But you kind of use these to get to here, if that makes sense. So a walk is just any way that you can move around a graph. It's just saying, okay, I went this way, I started here, I followed this edge, followed this edge, followed this edge, and then I went backwards this way, then this way, followed this loop. It's just the order in which you do things, like the edges and vertices that you follow, okay? Just how you're moving through a graph. You can overlap, it's fine. There's no big deal with any of that. That's a walk. A circuit is special. It is a walk, but you cannot visit the same edge more than once. You can't go back around along the same edge, okay? So you can't do that, but you can do something like this, okay? A circuit is a walk where you don't visit any edge more than once, and then you come back to where you started. Let's see if I can fit this. Okay, that's a circuit. It's a walk. You don't visit any edge more than once, and you come back to where you started. So this is a valid circuit. Go like that. Whee! Just like that. That's a circuit. That's a circuit. But this, this is not a circuit because I started over here. See that? Okay, paths and cycles. Those are the easier ones. Those are the ones that we usually talk about. For paths, you don't visit an edge or a vertex more than once. Okay? So let's see. Do I have a good example in this graph here of something that's not a path? Yeah, technically, parallel edges ruin everything, don't they? Let's add stuff, though. Let's add this one. That will help me. So this is, let's go back to green. This is not a path, but it's a cycle, because I'm visiting edges more than once. Visit this edge and this vertex, this edge and this vertex, this edge and this vertex. I can't go back along that, though. It's not a path that way, because I visited this vertex twice now. See that? That's the name of the game. So hopefully this all makes sense. Paths are usually what we care about. And then cycles are paths, but you can let the first and last things be the same. So you have no edge or vertex more than once except for the first and last. That vertex is okay to be the same. Okay? It has to be for a cycle. So that's a cycle. That's a cycle. This is technically a cycle. That is the idea. That's a cycle. That's a cycle. Plenty of cycles in this graph. Okay, so hopefully that all makes sense. Then graphs are fun because they can be like torn apart. You can have connected or disconnected graphs. A connected graph are like these, like this single graph right here. It's connected. You can get from every vertex to every other vertex. Totally fine. Disconnected graphs look like this. There's a disconnect. There are pieces off over here. Like pretend that this is all one big graph. This is like your graph G. These are disconnected because you can't get from like this vertex to this vertex. It's impossible. There's no edge. So that is a disconnected graph. If you have a disconnected graph, it's useful to talk about connected components of it. It's, okay, what are all the edges that I can get to from here? Like, they all are a component. What are all the neighbors that I can get to? All the people that I can get to. So that's one connected component. This is another connected component. This is a third connected component. Okay, hopefully that all makes some sense. And then I don't have enough room, so let's talk about regular graphs and then cliques and also kn and m. So, oops, let's get rid of that. So in a regular graph, everybody has the same degree. Okay? In a regular graph, every vertex has the same degree, so like this is a regular graph because every vertex has degree 2. I'll have 2 edges. Okay, that's a regular graph. And then cliques are the fun ones. Kn, this is like K4, let's do K4. You have a way to get to everybody else. It's a clique, everybody knows about everybody else. There's an edge directly to everybody. So this is saying this. We have that exists, everybody can get to everybody else. That exists, that one's already there, and then that one. There's a direct path from every node to every other node. Do that for everybody, they always exist, and go straight to any of these guys. That is a clique, or K4, okay? That's a clique on four nodes, 4 elements. Then, you can have this. It's like, they use K because it's kind of like a clique as well, but it's slightly different. K4-3 is like, on the left you have 4 nodes, on the right you have 3 nodes, and it's a clique in the sense that you can get from any node on the left immediately to any node on the right. Yeah? But never backwards, okay? It's just, this one can go to any of these. And so it's an easy calculation for how many edges there are. It spirals out like that. Okay? That's K4-3. This guy can go to any of these immediately. This guy can go to any of these immediately. Okay? That's K4-3. Those are your special graphs. Okay, let's talk about how you represent a graph now. So there's 2 major ways. If you have, let's make a simple graph with A, B, C, and D. So here's that, and maybe that. That's my graph. An adjacency list is just saying, okay, for every node, like this is the A node, what are all the ways, like what are all your neighbors? You just store the neighbors only. So A has B and C as neighbors. So there'd be a linked list here being stored. B has A, C, and D as neighbors. C has A and B immediately with edges that you can connect to. A and B. And then D has only B to get to. Okay? So that is your adjacency list. Adjacency matrices, those have a bit of wasted space because it's like you have to have an n by n matrix. And it looks like this, right? And then you kind of like section off, okay, is there a number here? Should I put it? What is the number to put here? It's a 0 if the edge exists. There are no self loops, so there's a 0 all over here along the diagonal. There's a 1 if it does exist, though. There is an edge from A to B, so between A to B, there's an edge, 1. Same, because it's a undirected graph, same from B to A. From B to A, everything's the same across this diagonal. And then C to A and C to B, so C to A and C to B, sorry, and it's flipped, so C to A, so A to C, C to B, so B to C, dot, dot, dot. Okay, and you can fill in this for the rest. Okay, it's just a 1 if there is an edge, a 0 if there's not. And that finally brings us to like circuits and paths and cycles with people's names attached to them. So I think Hamiltonian cycles and paths are the easiest one to talk about. So a Hamiltonian cycle / path is a path, or let's do cycle first. That one's easiest. So a Hamiltonian cycle is just a cycle that includes every vertex in the graph. There might be extra edges, doesn't really matter. So here is my Hamiltonian cycle in this graph here. I can just go this way, this way, this way, and this way. Okay? It's got to be a path. So that's a nice Hamiltonian cycle. And a Hamiltonian path is just a path that includes every vertex. So it's just take your cycle, drop this one. It's just this one like that, because you don't want it to come back around. So that's Hamiltonian stuff. And then Euler stuff gets a bit fancier because it has to include every vertex and path. And it has to be a circuit because you might come back to the same node. That's the idea. Okay? So if you remember that special graph, it looked like this with these edges. Let's see if I can remember how to do a Euler circuit. So it's like that, probably that. I guess it's like that. Okay, I think that worked. So containing every vertex and path, and it's a circuit because sometimes you can come back around to the same place. Okay, that is the idea. And oops, there was supposed to be a vertex there. Okay, so that is graphs in a nutshell. We have to speed along. I'm sorry, do come to office hours if you have any questions about anything particular. Let's talk now about trees. So lots of terminology for trees as well. Again, check the book, check the slides. But trees are either free, they're just sitting around. Whee. Boop, 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 boop. They're just chilling. Or, like, so there's no real structure to them. Or they're rooted. There's like, we've picked an element, we'll call this one the root. Okay? That's the idea. So usually we draw it in this way. If there's a root going on, you have any number of children, doesn't matter. Doesn't have to be a binary tree, be anything. So here's my tree. There's a lot of terminology here. There are levels. This is level 0. This is level 1. It's right over here. Level 0, level 1, level 2, level 3. Okay. The height is the maximum level. So the height of the tree is 3, because that's how many you have to go down to get to a leaf node down at the bottom. It's as far as you can go, as many edges as you can cross. That's the height of the tree is 3. Parents are, you go back up to previous levels. So like the parent of this node is this node. That's all. And you can go back up to like grandparents and things. So like the ancestor of this node is this one. Okay, there's an ancestor going along. And so with every parent comes a child. This parent has 2 children. This node has 3 children. And then opposite of ancestor is descendant. This one has a bunch. Every node in the tree is a descendant of the root, right? Every node in this subtree, every node in these 3 nodes is a descendant of that level 1 node. Leaves are just nodes. Leaves in rooted trees are just nodes with no children. That's all. So these are your 5 leaves. In a free tree, it gets a bit weird because they define leaves as because there's no root. It's just a node with a with degree 1, which looks a bit different. Like, so they're saying that this is technically, if this is a free tree, this has 2 leaves because this has degree 1, this has degree 1. Okay, that was a problem in your homework. Yeah, that's the idea. And then subtrees are just, okay, section off a tree and pick a new root. It's like, okay, this is my root now. So that means the tree becomes this. That's a subtree. It's a smaller tree inside of a tree. Okay? So lots of terminology. Hopefully it's all coming back to us. And probably the most important thing you can do to a tree is like visit stuff. Like use the tree, go through every node. So there are a bunch of different ways to traverse a tree. Let's talk about pre-order, post-order, in-order, and breadth-first search. So here is my simple little tree. Let's do it like that. A simple, very simple binary tree. How about that? That'll work. So this is, I don't know, A, B, C, D, and E. Okay, so pre-order and post-order remember what these do. So preorder is a recursive algorithm, same for post. It's always talking about the pre and post part means when does it recursively, like when does it visit the root? And pre means root first. Root, then children. Post means children, then root. And you visit the children from left to right. Okay, so let's do preorder traversal of this tree. It's, okay, visit the root and then all of its children. So we definitely have an A. And then we have to visit all of its children to the left and then recursively visit the children to the right as well. Okay, so we're going to recursively visit this tree now, rooted at B. So we're working on this tree. We see the B, it's root left, right. So B and then D and E. So we do recursively this, recursively that. There's only one node there, D and E. And then we're done with this one. We go to the right of the original node, and we have C. Okay, so that's the pre-order. And then the post-order looks like this. So it's always go left, then right, then talk about the root. So A is going to be the end. A is going to be at the end of this. So we're working on this subtree right now. It's always left, right, root. So it's D, E, B. And then we have the right subtree still, C, and then we have the root, A. Okay, hopefully that makes some sense. That's post order. In order is left, right, root. No, sorry, left, root, right. Excuse me. It has to be a binary tree. There has to be only left and right children. Whereas pre-order and post-order would have worked if I had this many nodes. Totally fine. In order, I'll let you do that one yourself. Maybe draw an actual tree with numbers in it. That would help. Breadth first search now. BFS. Gives you level order, so if I just ask you the order, you can just read them off. It's like, okay, it's A, B, C, D, E. Thanks to how I named this. Okay, so that's breadth first search, and this uses a queue. The rest of these use either stacks or recursion. Okay, those are tree traversals. Then there are special graph traversals that create trees out of graphs, like how it visited the nodes. Whee. So this is, let's pretend this is my graph. Boop, 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 boop. This is A, B, C, D, E. Let me name them weird just so that we can have something interesting. Depth first search for graphs is kind of like the equivalent of post order. It's, you use a stack or recursion and you just visit things. Okay, so let me draw you the DFS tree for this. And then we'll do BFS as well. Starting at A, let's say that we start at A. What we do is depth first search, it's always, okay, let's recursively visit all our children. Let's push our children to the stack. Okay, so we're going to then look at B, because that's the next one in order. Okay, alphabetical order. And then we'll add, okay, all the node that we haven't seen yet. We have seen A, so we can't go back along that edge, but we haven't seen E, so let's go along that edge. Let's go to E. And then that's the idea. This is what keeps happening. And then E goes to D. That's the only other one that hasn't been viewed. Then D goes to C. So that's depth first search. I don't know why I wrote that one at the bottom. I am sorry. Let's put this in order of depth first search first on the top. Whee. So that's a DFS tree. It was added in this order. This was first edge we crossed, second, third, and fourth. So we visited A first, B second, E third, D fourth, and C fifth. Okay, so it just tries to get to the bottom as fast as it can. That's what DFS does. BFS tries to stay close to the root, or the initial node, in this case. And this is always making a tree. Okay, this is a weird looking tree, but it's a tree. BFS, starting at A, it's going to, okay, let's visit the children in order. So we're going to visit the B. That's the first thing we visit, this is the second thing in order. Then it's like we add E to a queue as well. So we haven't been there yet. So now we add E, to the queue, and then we pop things off. Okay, so now we've been to B. Is there any node from B that we haven't been to? So no, the answer is no. So we continue. We're done. Add its children. Then we take E and we add any of its children to our queue that we haven't seen, so we're going to add the D. Okay, and so that will let us, in the next round of the queue, pop off the D and visit it. Okay, so that's the fourth thing we visit, and then this is the fifth thing that we visit. So the tree looks different, because this is trying to stay as close to A as possible. It's kind of going in level order, if that makes sense. Okay? Because it's making a tree at the end of the day. So that's BFS and DFS. And that is our tree knowledge. Graph traversals are in this section because graph traversals make trees. Okay, so we only have 2 things left, but they have quite a few slides because there were a lot of topics in those chapters. So that's what we'll come back and do in the next lecture. Okay, so I will see you there.